In this series, our goal is to tell the story of how numbers grow. We start with the natural numbers, the numbers that came from the human need to count, and ask a simple question at each step. What forces us to go further? What breaks? What becomes unsolvable? And what new number system do we have to invent to fix it? This thread will carry us from natural numbers to integers, to rationals, and to reals, and finally to complex numbers. To tell this story well, we need to be on the same page about some vocabulary. And that is what this video is for. We will cover relations, what they are, how they are defined, and the properties they can have. In the next couple of videos, we will build on this. We will first cover equivalence relations, then functions, and then cardinality through the lens of functions. By the end of this, we will have everything we need to start constructing number systems from scratch. I'm not going to be exhaustive with respect to my examples when I deal with relations, functions, and cardinality. The idea is to choose examples so that it makes the definitions vivid and concrete. If you have seen these definitions before, think of this video as sharpening something you already hold. If you're seeing them for the first time, the examples will do the work. If you're comfortable with the notion of when binary relations are reflexive or symmetric or transitive, then feel free to skip this video. Having said this, let's start. In the previous lecture, we saw how the idea of a set evolved and how ZFC axioms were introduced to eliminate the contradictions that naive set theory ran into. For everything we do in this course, we will work with the naive definition. A set is a collection of distinct, well-defined objects, remember. But it is worth keeping in mind that ZFC is always standing in the background, making this intuition precise and free of paradox. In particular, we will only create sets from sets that we already know exist. In our previous video, we briefly touched on the fact that Cantor was studying the size of infinite collections of points on the real line. To understand how big is an infinite set, we need to build the right tool to answer it, which is a particular kind of function. And to understand functions properly, we need to start one level below with relations. So before we go into relations, I just want to cover a couple of notations. So the first is the how do we represent sets? So we can either represent them as in the list form or in the set builder notation. So you might have seen this, but I'll just cover it so that when I refer to roster form or set builder notation, it's clear what I mean. So roster form means just that we list out the elements of the set. If the number of elements are too much, for example, in this case, where we have listed all the alphabets in the set, note that this is a finite set, but we put these three dots in between, which is sort of like an understanding between the author and the reader, saying that the pattern is clear enough for the reader to understand that these three dots mean that the pattern continues from C onwards, D, E, and so on. And then we put a Z in the end to show that the pattern completes at Z. The set builder notation is a different kind of notation for set where we fix a property and we say the set of elements that satisfy this property. So, but remember that we will always choose set of elements from a set that we already know exists. So this is for the ZFC axioms that we encountered in the previous videos. So for example, we can say that the set of real numbers x such that x is, let's say, natural number, because we have seen natural numbers and it's easy to understand. So x is a natural number such that x is greater than 10. So we are creating a set from the set that we already know exists, the set of natural numbers. And from there, we are saying that we are only picking all the natural numbers that satisfy greater than 10 property. So this is a set builder notation. So, and this is a list form. Having made this clear, let's begin. So suppose you have two sets, A and B, and you want to capture some notion of connection between the elements of A and the elements of B. Then what is the most general thing you could write down? The idea is to just list the pairs down, and that is what is a relation. So these are known as binary relations. We only cover binary relations in our discussion. So a, a we say A is related to B, and we denote this as the pair A comma B, an ordered pair A comma B. So we will see the formal definition of a relation now. So a binary relation from a set A to a set B is any subset of the Cartesian product A cross B. So let's just quickly go over what is a Cartesian product. Most of you might know what is a Cartesian product. So given two sets A and B, their Cartesian product is the set of all ordered pairs A and A comma B, where the first element comes from A and the second from B. So the ordered pair here just means that the first comes from A and the second comes from B. So that is here A belongs to A, which is here, and B belongs to B. That is what it means by an ordered pair. Um, I just want to emphasize that this here is a set builder notation. Okay, let's see some examples of relations. So the first two examples that we will cover, they are Cartesian products. Since a subset is since a set is a subset of itself, a Cartesian product is also a relation. So it's a Cartesian product and relation. So the first set that we are looking at, the first example that we are looking at is where A is the finite set consisting of just three numbers, 1, 2, 3, and B is a set consisting of two characters, A comma B, and their Cartesian product is as follows. 1 is paired with A and B, 2 is paired with A and B, and 3 is paired with A and B. Similarly, we have the Cartesian product of these two sets, 0, comma 1. This is an example where both A and B are the same. So here A is equal to B. We will see that we will see that we'll cover this in detail. When A is equal to B, we have we look at some interesting structural properties that can exist. Um, so we'll come to that. So this is essentially known as the four. So this we encounter quite often in digital logic. It's called the four possible inputs to the 2-bit logic gate. Similarly, we have an example of a relation here. This is not a Cartesian product. So this is an example where the relation we are considering is not a Cartesian product, but it's just purely relation. So we have two sets, 1 to 26 is the first set, A. B is the list of all alphabets in the English language, A to Z. And if we had to consider the Cartesian product, then it would contain 676 possible pairs. This is actually 26 into 26. But the above relation S just pairs each integer with exactly one letter. It's the position in the alphabet. Position of the alphabet in the order that we say. Okay, so when A is equal to B, we say the relation is on A. So we say that the binary relation is on A. So this is a special case, and this is a very interesting case. We will see its structural properties soon. So here we have two examples. One is the less than relation. So if we the relation has three pairs, 1 comma 2, because 1 is less than 2. Similarly, we have 1 comma 3 and 2 comma 3. We can see that 2 comma 1 doesn't belong to this relation because 2 is greater than 1. Even 2 comma 2 doesn't belong to S because 2 is greater than equal to 2, or 2 is equal to 2. So, but this says strictly less than. Similarly, we have another example, divides relation. So we can see that this relation contains A comma B if A divides B. So 1 divides 1, 1 divides 2, 1 divides every number. So we have 1 paired with everything. So 1 to 6. And then 2 divides 2, 2 divides 4, 2 divides 6. So we have 2 comma 2, 2 comma 4, 2 comma 6. 2 comma 6. Similarly, we can work out the remaining entries, remaining tuples. So now let's cover some interesting structural properties when it is a binary relation with A equal to B. So when a relation is on a single set A, we can have some structural properties. The first one we cover is the reflexive property. So reflexive requires that if S is a relation on A, then for every A in A, we have A comma A in S. So if if S is a reflexive relation, every element is related to itself. So let's look back at the divides example that we considered in the previous example, in the previous page. We can see that since A divides A for all A in 1 to 6, 1 comma 1 is there. So this is a reflexive relation. So you can quickly check 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there, 4 comma 4, 5 comma 5, 6 comma 6. So this is a reflexive relation. Similarly, we have symmetric relation. So a relation is, so S is a relation on A, and this is symmetric if it satisfies the following property. So if A comma B is in S, then B comma A is also in S. Remember that I just want to emphasize here that relation is ordered. So by default, A comma B in S does not imply B comma A in S. So in the previous example, for example, you can see that 1 comma 3 was in this relation, but 3 comma 1 is not in this relation. But the example that we have here, same remainder mod 3, we can quickly check that this is a symmetric relation, because if, for example, if 0 comma 3 is there, 0 and 3 mod 3 have the same remainder. So 3 mod 3 is basically 0. And so mod, just want to, if mod is not clear, then this just means that mod 3 means A mod 3 means A percent 3, which means the remainder of A when divided by 3. So as you can see that 0 and 3 have the same remainder. So 3 comma 0 is also related with each other. And this is very easy to check that this is a symmetric relation. The opposite of this is the anti-symmetric relation. So this is also an interesting property that ordered sets exhibit. We will not cover them, but I just thought it's good to state it for completeness. So if S is a relation on A, and then for every A comma B in A, and if A is not equal to B, so this is also an important condition that we should see. It doesn't hold for A comma A. It just holds when A is not equal to itself. So A not equal to B. So these are different elements. So if A comma B is in S, then B comma A is not in S. So this is like directly saying that the opposite side should not be in S. So what I mean is if 1 comma 2 is in S, then 2 comma 1 is not in S. And as we saw the divides relation before, if A divides B, then B does not divide A if A not equal to B. So we can quickly check that this is an anti-symmetric relation. So finally, we have the transitive relation. So if S is a relation on A, and for every A comma B comma C in A, if A is related to B and B is related to C in via S, so then A is related to C via S. This is just the transitivity property which says that A is related to B and B is related to C, then A is related to C. So I've written it here, A and A. So this essentially divides relation that we saw before. If this is a transitive relation, this is also again easy to see. If A divides B and B divides C, then A divides C. Easy to check is if 1 divides 2 and 2 divides 4, then 1 divides 4. Similarly, if let's see if, yeah, so if we can do like a small example where we have 2 divides 6 divides 6, but again, then 2 divides 6. So in this case, essentially, D is equal to C. So it's easy to check that divides is also a transitive relation. So in the next video, we will cover equivalence relations and we will define algebraic operations on equivalence classes. And this construction will be new for many people. It would it would essentially this kind of construction of defining algebraic operations on equivalence classes appears a lot in math and also uh, other algebraic techniques used in computer science. And it once you understand this construction, it helps you connect with techniques across other areas in computer science. Thank you. See you in the next video.